And also because many physical property or behavior, there's scattering, optical signal, many different reality, they are complicated, is more complicated than X-ray, then you have much more challenges. But all this, we have achieved that to some extent. Of course, it's never good enough, the solution. It can always better. So what we have done, we have a good, good discretization that really preserve the good, correct behavior of the true solution that use mathematics. An efficient iterative solver, not a very brute force one that use mathematics, works for general geometry and boundary condition. You need mathematics. Nowadays we can do such a problem instead of years. We can do it in about hours. And of course, we can utilize massive parallel computers to do this to further improve. Okay, this is typical result, what we can do. Okay, so I think this is coming to the question of how to recover this. Again, even I know how the forward model does, I need to do, say, from the mismatch, how do I correct my guess? Okay, that's where the key point of the inverse problem. And then you have to minimize the mismatch. Okay, so this is what my forward problem predicts. What's the measurement? This is the true measurement. I want to minimize the mismatch. And that is, again, a huge challenge problem. It's optimization. And I don't want to say too much in detail about this. It's even more challenging than this. Than the forward problem. This is our result. For example, if you have something, object looks like this and this with different optical property, of course, it's a very complicated model. You see something like this, and this is corresponding to that. And this is in a more realistic geometry, and the two, for example, tumors with some kind of special optical property, you can see them into here. Okay, the current work where there are many things we want to do. The most important thing, we're ready to work with real data from the real experiments. We're also going to apply our method to this molecular imaging type of problem, which is very similar, and combine this optical tomography with some other modality, ultrasound, CT, and so on and so forth. Okay, with that, I think I will skip this, the optical control things, but this has something to do with finding if you have this, you know the traffic, you know the road condition everywhere. How do I find the optimum path, in a sense, the shorter way to exit this domain? Okay, then how do I find this path? How do I know from each location what's the shortest time I can reach the boundary? And this is also related how the earthquake propagate in the earth and so on and so forth. But I think I don't have much time. I reduce to this one-line mathematics equation. But there are a lot of mathematical difficulty, but we have developed a very efficient one. This is, I would say, one of the fastest algorithms for this type of problem in the world. Okay, so it's have been widely used in many applications in science and engineering. Also, I want to emphasize that as a mathematician, we're never satisfied with just providing an algorithm. We want to provide analysis to tell you why it's the fattest one, why you can trust on it, the error is not so big, the old mathematical analysis behind this. Okay, so with that, I want to draw a conclusion to my part. And here I want to make acknowledgement that the funding agency I have received support so far, National Science Foundation, Office of Naval Research, DARPA, and MURI. And the collaborator and the student and postdocs, those in blue are related to the topics I talked about today. And the last one, of course, is thank you for your attention.